Alper, are you able to start now?
Yeah, sure.
Okay. So I would like to thank you again very much for spending time to prepare this. It is very useful, I think, to promote the use of FRP in the field of construction for students and also researchers. So I'm very pleased to have you in this session today, and so start whenever you are able to do it.
Okay. Thank you, Emmanuel. It's my great pleasure to have this webinar with you and the colleagues. I should tell that that's my first time doing such a kind of presentation. So I hope everything will be okay. So if there's something wrong, please excuse me. So now let me begin with the introduction of the topic. I'm going to talk on seismic retrofitting of reinforced concrete structures using FRPs. I will briefly summarize some of the work that we have carried out in Istanbul Technical University, mostly on reinforced concrete columns, as well as on beam column joints, which also include some three-dimensional reinforced concrete frames as well. So I already discussed about the content of the presentation. Basically about column retrofitting, I will present two different types of studies. One is on confinement of concrete on large-scale columns, reinforced concrete columns. And the other is using longitudinal reinforcement through FRPs to increase the bending moment capacity of columns under seismic type loading. And also, I'm going to discuss about retrofitting of beam column joints, as I have mentioned before. Most of the specimens, which are almost full-scale, real-scale numbers, represent the common deficiencies which we frequently encounter in Turkey and many developing countries. Because we believe that these types of structures are the structures which are in need of urgent retrofitting other than kind of better structures. So almost all specimens, I'm going to discuss on them with details, but generally they are constructed with low quality concrete, which represents a great majority of the buildings in Turkey and in many other parts of the world. They are generally hand mixed, and their compression strength is something like between 10 to 20 megapascal. And usually the stirrups are largely spaced, like in the order of 20 centimeter, 25, 30, sometimes even more. This is just one example. So most of the specimens that I'm going to present today have this kind of details. And also, as you see here, the hooks of the stirrups have have bent only 90 degrees, and they are generally short, like 5 centimeters or 4 centimeters. These are the kind of deficiencies which you need retrofitting, and where FRPs can be effective in terms of better seismic performance. So again, like most of the existing structures which need retrofitting in actual life, we generally use plain reinforcing bars, which represent the construction at the years, maybe 20 years ago, 30 years ago. Also, sometimes there are some problems about left supply snaps. So if you look at briefly to the use of FRPs for seismic retrofitting, we can talk about some general issues that most of you should be familiar. There are advantages in terms of high strength to weight ratio, and also they are very good because the geometry doesn't change, which is often an important concern during retrofitting. Peak applicability is also very important because the inhabitants consider that if they have to leave the building a long time, then that's not preferred. And also the efficiency is very high in terms of strength and ductility, particularly when you are dealing with substandard reinforced concrete members. On the other hand, like everything, they have some drawbacks, like poor performance at high temperatures. They are relatively higher cost with respect to conventional retrofitting techniques. And chemically, there are some problems about the workers' health and limited applications, potentials in case of wet surfaces and low temperatures. Sometimes there is incompatibility between the composite and the substrate material. So, first I'm going to talk about retrofit in terms of providing external confinement to the column. And I'm going to summarize two different types of experimental studies. One is confinement with FRP sheets, which we kind of indicated this by experimental study 1. Second is confinement with TRM, which means textile reinforced mortar, and FRCM, which is fabric reinforced cementitious matrix composites. So for the columns, I will briefly show these two types of experiments on confinement. As I have mentioned before, I'm going to also talk about flexural retrofit of reinforced concrete columns, and for that, I'm going to talk about longitudinal use of FRP reinforcement. If we look at experimental study 1, which is seismic performance of full-scale FRP confined substandard columns. These are the columns we tested, and currently one of these columns are being tested in the laboratory by one of my PhD students, because it's a much larger set of experiments. It includes different column sizes with cross-sectional aspect ratios from 1 to 4. There are different other parameters, like loading in strong direction or weak direction. So it includes maybe more than 30 columns, all full scale. But I'm just today going to talk about 3 of them, where one of them is the reference column. Here 35 means that axial force on the column is about 35% of the axial load capacity of the column. And then I'm going to summarize the results of 2 columns, which are either retrofitted by 1 ply of FRPs, carbon FRPs, or 2 plies of FRPs in transverse direction. And as you see here, obviously we tested those columns on the constant axial load and reverse cyclic lateral loads. So this is the configuration of the specimen. As you see, that's a cantilever column. The column dimension is 30 centimeter by 60 centimeters. And concrete strength is 16 megapascal. Yield strength of the main bars is 310 megapascal. I have already described the column cross-section sizes. We have about 1% reinforcement ratio and longitudinal direction, which is 10 bars of 40 millimeters. And the lateral reinforcement is 20 centimeters space, 10 millimeter bars around here, which are the most critical areas. And for retrofit of these kind of substandard columns, we use CFRP sheets with given characteristics here. I should say that we have no overlap bars here for those specimens, just to eliminate the potential effects that could change the behavior. So we don't have any problems about lap splice deficiencies or lap splice lengths. So that's the result of the reference column. As you see, this is total failure. The specimen lost all axial load capacity, not only lateral load capacity. And this happened at around 2% drift ratio, lateral drift ratio. I should say that bar buckling was observed at around 1.5% lateral drift. Finally, at about 2% drift, the specimen lost its all axial load capacity, which means that the structure would collapse if this kind of drifts are demanded from the structure during the earthquake. So apparently this damage mechanism tells us if you have confined this area, which we did for the next specimens, you could go to much better seismic performances. We're going to the retrofitted specimens. Here you can see the load displacement diagram for the column, for the reference column, as you see where totally lateral load resistance is lost. Here, this is a load displacement relationship Vertical axis is showing us the loads, lateral loads applied on the column. Horizontal axis is the displacement or drift ratio, 1% drift ratio. As you see here, the specimen began losing strength at around 1% drift ratio. Then we have buckling of bars at about 1.5% drift. And at the point of E, strength is lost about 15%, which means that the drift capacity is only 1%. Then, before being able to reach the 2%, there's a sudden and large loss of strength, which ended up with loss of all axial load capacity. This is reference specimen. We go to the specimen, which is confined by one ply of FRPs, as you see here. This is the appearance of the retrofitted specimen at the drift ratio of 3%. As you see, again, we have some buckling of longitudinal bars in compression zone. And obviously, it may be interesting to see that since axial load is high, the compression zone is quite large. Therefore, we have buckling not only in the edge bars, but also we have buckling in these bars as well, which are close to the middle of the section. And another thing to be important is that, as you see, the stirrups were already open, which has only 19-degree hooks. Whereas it has provided some constraint in terms of buckling of longitudinal bars. Still, it's open at this point. So if you look at load displacement diagram, which is obviously better than the reference specimen, you see we could go up to 3% drift, where rupture of FRPs were observed. And of course, upon rupture of these FRP sheets, FRP jacket, the strength is lost again quite suddenly. But you can notice that we didn't experience strength degradation at around 1% drift, even at 2%. Failure was just around 3% drift ratio. So obviously we had much better performance. The energy dissipation capacity is much better, which means that this retrofitted column could survive the same earthquake, or could performance a much better performance than even stronger earthquake. If you look at the column with two plies of FRP sheets wrapped around the column confinement zone, this photograph shows us the appearance at 5% lateral drift, almost more than double of the reference specimen. Look at the load displacement diagram. As you see, we could go up to 5% drifts without a substantial loss or without a significant loss in strength. But stable hysteresis loops, around 5% drift again, upon rupture of FRP sheets, as expected, the strength is lost suddenly. But you can see the obvious improvement in the behavior. And if you look at the envelope curves of these three specimens, you can notice the very significant enhancement in the behavior. But I should say that, of course, this horizontal curve could be misleading. Don't forget that this specimen also lost its strength at around this point. Anyway, we had the failure, but the failure was much retarded in case of the column with two plies of FRP jacket. So now let's have a look at the columns that we use textile reinforced mortar and fiber reinforced cementitious matrix rather than using carbon fibers and epoxies for the matrix material. Just to introduce the methodology, what we did for the repair and for the retrofit of these kind of columns. This is just showing on small size cylinders, but I'm going to show you the larger size columns. Firstly, we repaired the defects on the surface of the columns. We cleaned the surface. We rounded the corners to a radius of 30 millimeter. First, that's valid for rectangular sections. And then what we did, we sprayed, I should say that this is a kind of sprayed concrete. We sprayed the glass fiber cementitious composite. And then we applied the first layer, and maybe in the next slide, it's better. And we applied basalt textile in this case, but we also use carbon textile and other types of materials. Then we applied the next layer of sprayed GFRC, which is glass fiber reinforced concrete. So each layer is about half centimeter, 5 millimeters, which includes a layer of GFRC and a layer of basalt textile mesh. At the end, you have such kind of appearance. Some information about the materials that we used. If you look at glass fiber reinforced concrete, this has a flexural tensile strength about 15 megapascal and compression strength of 44 megapascal. And if you look at basalt mesh, this has the mesh size of 25 millimeters in two directions. Elastic modulus 32 gigapascal. Quite high rupture strain, about 5%. And tensile strength is about 1,600 megapascal. I think I don't have that slide, but if we use it like a composite material with this GFRC and basalt mesh, we have some value of about 7 megapascal for tensile strength. That is how we applied it in case of columns. These columns were 20 by 30 centimeters. Not full scale, but I could say nearly full scale. And they were constructed with 10 megapascal concrete, substandard concrete. We used plain reinforcing bars, both for longitudinal and transverse bars. And we had different types of transverse bar spacing, going from 60 millimeter to 180 millimeters. This photograph shows one with 90 millimeter scuff spacing. But as I said, first, this kind of retrofit was much more effective when we look at the behavior of widely spaced stirrup cases. So here you see how we applied this kind of application. And I should repeat again, this application is done by spraying the concrete, like kind of shotcrete. So this is the test setup in the laboratory of Istanbul Technical University. Again, a similar test setup where we have tested the FRP jacketed reinforced concrete columns. This time the specimen height is a little bit less and the cross-sectional dimension is again a little bit less. But an interesting thing about these columns is we applied quite high axial loads, which were about 50 to 70% of the axial load capacity of the column. Of course, obviously, these high levels of axial forces are not permitted by the seismic standards and even for the reinforced concrete standards for vertical loads because of some creep effects. In Turkey, we have a lot of this type of columns because of the unforeseen low quality of concrete. Because during design, engineers assume that their concrete will do, say, 25 megapascal, 30 megapascal, whatever. But at the end, you see that concrete is about half. This means that the axial stress on the column or axial load on the column, while axial load is same on the column, axial stress is much closer to the axial capacity of the concrete. Therefore, these values are not exaggerated values. We have many columns like that in practice, and most of them are suffering during earthquakes significantly. So among these type of columns, I'm going to show some results from reference columns. And the column confined with 3 layers of basalt textile and GFRC. And 3 layers mean, if you think that one layer is about 5 millimeters, we have a jacket of 15 millimeters, which has 3 layers of basalt sheets and also 5 millimeter thickness of GFRC between these 3 plies of TRM or basalt textile. So if you look at 2 specimens, on the left you see the reference column, on the right you see the retrofitted column. I should say that that is not the worst reference column because this column had stirrups with 90 millimeter spacing. You can imagine what the behavior would be in case of 80 millimeter space stirrup cases. It was much worse than this one, but in this presentation I'm showing these two specimens. Nevertheless, you see the degradation in strength at about 2% drift, significant losses in strength, and finally, for going further drifts, for the lateral displacements, you see the substantial loss in axial load capacity as well. So all lateral load capacity was lost. Also, the specimen was kind of out of control while making this kind of loading. On the other hand, if you look at the retrofitted column, here you can see the appearance of this column as well. Just a jacket of 1.5 centimeter thick. And as you see, this was applied on the potential plastic hinge regions, somewhere here, not touching to the foundation, to avoid direct axial loading of the jacket. So the jacket was basically subjected to lateral stresses, I could say. And the jacket was only responsible for providing lateral confinement, improve particular ductility. So I think I already described the damage of reference specimens with rupture of stirrups, buckling of main bars, and total demolition of concrete after loss of this transverse reinforcement. On the other hand, this specimen retrofitted with this kind of jacket contains load resistance capacity up to somewhere like 8% drift ratio, which is quite high for a typical earthquake, even for a typical severe earthquake. A severe earthquake could demand from a typical reinforced concrete frame structure. And if you look at this, the envelope curves, here, of course, you could say that, okay, there's not too much difference, but just remember that after this point, curve went like that. So there was no more displacement capacity for this substandard specimen, whereas we could sustain much larger earthquake with the column, which is kind of jacketed simply without too much sophisticated intervention. So we somehow summarize confinement with textile reinforced mortar and fiber reinforced cement matrix. We have good application rate because of spraying of GFRC. And performance of this type of retrofit is also good in case of even high temperatures, which is kind of weak point of FRP jacketing. And there's no harm or less harm to workers' health. And it's also cost effective because you use kind of simpler material or use less amount of expensive materials. So I can say that preliminary results of two parallel experimental programs demonstrated that significant enhancement can be obtained on strength and ductility of substandard reinforced concrete structural members, making use of this kind of retrofit jacket, I could say. So there's another application which has totally different target. That also targets to retrofit columns under seismic actions, but this time the target is not enhancing the ductility, but the target is increasing the flexible capacity. Sometimes you need this kind of retrofit as well. So this is kind of indicated as experiment study 3, and I'm going to summarize this study to you. So don't forget that this time basic target is improving the flexural capacity, not the ductility. So you will see that we are going to add some longitudinal bars and anchor them to the foundation to increase the moment resistance capacity in the potential critical zones. This figure shows the characteristics of the specimens before retrofitting, of course. The column dimensions are like the smaller of the ones I have showed you before, 20 centimeter width and 30 centimeter depth. Again, we have about 1% longitudinal reinforcement ratio, which is obtained by 40 millimeter bars, and number of the bars are 4 bars at the corners. Again, we don't have an overlapped connection between the footing and the column, so the bars are continuous from the foundation to the top of the column. And again, we have weak confinement here to represent most typical weak columns. Therefore, we have 20 centimeter space, 10 millimeter diameter long transverse bars. Of course, again, we have axial loading and also reverse cyclic lateral loading like the previous test I have shown. That's another PhD study, by the way. One of my students are working on that and about to complete his PhD. I think already we have written 2 papers about these. They are already can be achieved in several journals. But some other parameters are also being examined, like usage of hybrid use of the FRP bars to make benefit of different characteristics of FRP bars. And also we included some column tests for which we have used transverse loading in weak direction. In general, we have the columns tested in long direction or strong direction, but of course, they will be subjected to seismic actions in weak direction as well, so their performance is also of interest. Just I'm going to show some results here, or summary of the initial results. Again, different types of bars are used: GFRP bars, aramid fiber reinforced polymer bars, and CFRP bars, also AFRP laminates, and CFRP sheets. As you can guess, these bars or laminates are used for longitudinal bars or longitudinal retrofit or flexural retrofit, I could say. And CFRP sheets are either used for anchoring purposes or for transverse jacketing of the columns. Because when you apply longitudinal FRP bars or laminates, then your flexural capacity increases, which could cause shear failure, which of course you never would like to have. Therefore, considering the capacity design principles, we increase the flexural capacity using any sort of technique. We should also take care of shear strength by, for example, jacketing with CFRP sheets in transverse direction. I'm not going to spend some time on discussing on the characteristics of materials that we have used. It's here, and I think this video will be accessible on the web page of IIFC. Passing this slide. I think most of you are familiar with those values. So some photographs from production phase. Holes for connection of the column to the footing of the laboratory. Some strain gauges, reinforcement cages in the laboratory, and the concrete cast. This shows how we retrofitted 3 of the columns. As you see, for this one, we had put 4 AFRP reinforcement bars to 4 corners, and the 4 AFRP bars were anchored to the foundation through holes that were later opened on the foundation. So the bar itself, AFRP bar itself, has been anchored directly to the foundation. And as you see here, we also use some transverse CFRP jacket that I mentioned before for the purpose of shear retrofit. As well as, of course, to avoid buckling of buckling of AFRP bars and steel bars, as well as to provide some more confinement to have better ductility characteristics. The next specimen here, as you see, we have those 4 AFRP bars like the previous one. But in addition, we have some additional bars which are used for only anchoring purposes. Of course, nevertheless, they will have some contribution to flexural capacity as well. But the target is to avoid some anchorage failure at around this zone. But this solution is a little bit more costly with respect to this one. And the final type that I'm going to present to you in this presentation is the one where we have intentional partial debonding of AFRP bars at the top of the foundation here. The reason is that we saw that in most cases, because of concentrated high strains, FRP bars or laminates are fractured at this point because of obviously the maximum moment. And we thought that if we could distribute the strains on a larger part of the FRP bars, strains will be less for the same drip, for the same top displacement. Therefore, the fracture of the FRP bars could be retarded to a certain level. So the target was that. And this type of specimen is called partial debonded column, you could say. Other than these details, the retrofitting scheme is similar. But I should say that, of course, that's a kind of different technique because, as I'm going to show in coming slides, what we did first before applying this technique is to remove the cover concrete. We just broke the concrete because you know that these are poor quality specimens. Therefore, concrete is poor quality. Then it's not a big work to remove this poor concrete because if you don't have a good concrete here, then debonding of these AFRP bars would be inevitable because of the poor strength of concrete. Even though you use very high quality epoxies or whatever you like, since the concrete quality is poor, the concrete would be delaminated from the cover itself. Therefore, as I'm going to show you in coming slides, the first stage of retrofitting was removal of the cover concrete. And as I'm repeating again, since we are dealing with very low quality concrete, that's not a big deal. You could do that easily. And in practice, often when you have such kind of column, another problem is related with the corrosion of reinforcing bars. So these are old columns, not well protected because of the poor quality of concrete and often because of lack of sufficient maintenance and repair work. In Turkey, generally, if you want to deal with a column, first thing you have to do is to repair the damages related with corrosion. Therefore, you have to often remove the concrete cover and clean the reinforcing bars, and then, based on the level of corrosion, you have to decide what to do. So this is often an inevitable stage of retrofitting in many cases in Turkey. So after that we just apply a very thin layer of cement-based structural repair mortar to obtain a flat surface where we are going to place the either laminates or rods to retrofit the column in terms of flexural resistance. So we have this kind of mortar here. This is very, very thin, only covering the main bars and the transverse bars. So now the section of column is smaller than its original sizes because not all cover thickness have been produced again. And some roughening on the surface to have better bond with the next stage. Go ahead. And what we do is we use epoxy to bond the either laminates or rods. You see the rods here, laminates here, to bond them on the surface. But the surface is now a better quality of surface. It's the kind of high strength cement-based repaired mortar, not poor quality concrete. And that's very close to the main reinforcing bars. And we use the last layer of structural repair mortar, which is again a much better quality than the original concrete. Now the geometry of the column is equal to the initial geometry. So again, we don't change the geometry. All the intervention has been done within its original dimensions. The final stage, as I said, since we have increased the flexural capacity, avoid shear problems, we just apply a transverse jacket by CFRPs to improve shear strength. That test setup is quite similar with the works that I have shown you. We have reverse cyclic lateral loads here, axial load here, which is kept constant. Here you can see the locations of strain gauges on FRP reinforcement, anchorages, or the main steel bars. This is the loading system as often done. We apply the reverse cyclic displacements in two directions in a quasi-static fashion. So this is a summary of results, but I'm going to show you some graphs, so I don't want to spend some time on this table. So this shows us specimens where we use the FRP bars without any additional anchorages. This triangle one. And this is the one with the anchors, square one, which is a little bit better than all. And this one with the circle is the partially bonded. Not too much difference with respect to the one without additional anchors. But anyhow, if you look at the performance of the reference specimen, if you compare the retrofitted ones, as you see, up to 3% drift ratio, performance is much better in case of retrofitted ones. But upon reaching 3% drift, then we have the fracture of longitudinal rods or laminates, and then strength is lost. So we have almost the same strength at around these drifts. Then with increasing drifts, because we don't have confinement in the reference specimen, of course we lose the strength. Up to this point, because of totally contribution of transverse CFRP, we have a ductile behavior. So basically I could say that because of the longitudinal FRP bars, we have a strength increase like that, which is quite significant, up to double. In case of the bar, which we have additional anchors. And then we have, again, the degradation strength, and then much ductile behavior due to presence of the transverse CFRP sheets. So, as I said, we applied different techniques, different materials, different applications like hybrid application, different AFRP, CFRP, GFRPs to make benefit of all of those. And as you see, if you compare the behavior with the reference one, we have really significant increase in strength and you could say deformability, displacement capacity through different usages of this kind of retrofitting technique. I think this kind of, although it's kind of similar to near surface mounting application technique, this is kind of different one, and I don't know any other example which is exactly done like that. I'm not going to repeat the same things, but this is kind of similar behavior. You can see the significant improvement in strength, sometimes deformation capacity as well. These columns are loaded in the width direction. So this time 30 centimeter was the width and 20 centimeter was the depth of the column. It again shows the similar case in case of usage of hybrid FRP bars in width direction. I'm going to pass those details. I want to save some time for the joints. So I'm not going to talk on those details, but anytime this one, or we can anytime ask questions about details of these test results. Here you can see some ruptures of the FRP bars. This is somehow we don't like because you know that the elongation capacity of these bars are not that high. But on the other hand, this fracture shows us that we have efficiently used these AFRP bars until their failure. So no debonding or no other kinds of failures, which means that we can make use of the total capacity of AFRP bars. This shows this is a kind of hybrid retrofit. Then we have both an aramid rod and a glass rod. You can see different types of failures in these two different bars. Here you can see the failures of the laminates. These are aramid laminates. Sometimes we have total rupture. Sometimes we have kind of decomposition of the fibers, but not total loss of strength. So of course that's a kind of better behavior because that's quite sudden, whereas strength is lost a little bit more gradually in this case. So with that, I want to move to the retrofit of beam column joints after giving some brief explanation about the column tests. As you know, generally the exterior columns, or more commonly the corner columns, are the most vulnerable columns during the joints during the earthquakes. This has been shown by many observations that were observed after the earthquakes. In many cases, we have problems about it. And in many cases, there is no stirrup, no transverse reinforcement at the joint between the columns and beams because of difficulty of workmanship at this point. Of course, I'm talking about structures built 20 years ago, 30 years ago. Nowadays, even though it's difficult, the quality inspectors provide the transverse bars within the joint as well. So there are different types of failure modes. I'm just going to briefly touch this point because test results are somehow related with these ones. J-type failure is joint failure itself. EJ-type failure represents beam yielding first and then joint failure. TJ-type joint failure represents column yields first and then joint fails. ECG-type column and beam yields and then joint fails. AJ-type failure on the joints is buckling of longitudinal bars within the joint. J-type failure is slip of beam longitudinal bars followed by joint failure. S-type failure is only the slip of the beam longitudinal bars, so no problem in the joint. P-type failure is the beam yielding damage mechanism, no joint failure. And C-type failure is also again column mechanism, I could say no joint failure. So for the joints, we could say that we have mainly two mechanisms, either because of the failure of concrete strut in compression or because of the exceeding of diagonal tensile strength of concrete within the joint, if you don't have joint transverse bars. And this is the case what we are examining because we have a lot of this kind of structures. So if you look at J-type failure, where we have the joint failure itself, if we didn't have this kind of problem about the joint, or if we have sufficient joint strength, then the behavior would be like that. But in case of domination of the joint behavior, then we might have this kind of behavior, which is reflected by a lower strength as well as a significantly reduced ductility. And if you look at BJ-type failure, which means that our joint strength is actually higher and the beam yielding strength. However, with the yielding of the beam, with the increasing deformations, then the joint also fails. So we have such failure mechanism. We have little bit ductility, but then because of the joint shear failure, we have a reduction in ductility. I'm going to show some test results related with all these kind of failures. It's J-type failure, which means that slip and then joint failure. So there are three curves here. One is what would happen if the beam yielding would govern the behavior. And this shows what would be the behavior if the slip of beam longitudinal bars would govern the behavior. Okay. Here, what happens if we have also some problems within the joint? In the specimens tested by Bedirhan, which was my previous PhD student, the behavior was first governed by slip of longitudinal bars of the beam, negative moment area, and the slip caused deformations at a much lower strength, never reaching to yield strength of the beam or never reaching the shear strength of the joint, which is somehow good because if we reached shear strength of the joint, then the behavior would be brittle. Nevertheless, we have such a kind of pseudo-ductility until a certain displacement, and when we reach to the point where the shear strength is reduced to the same point, and then the shear behavior of the joint governs the behavior. So in total, we have this kind of partial ductile behavior and then a brittle failure, which is at much lower load with respect to the beam-dominated behavior. So that's what could happen in case of longitudinal bar buckling when you don't have sufficient amount of transverse bars. These all show the importance of necessity of some kind of retrofit on the beam column joint areas when you don't have transverse reinforcing force. So we could have, in case of FRP retrofit of joints, we could have basically two different types of failures. One is called, we could say, FRP debonding. The other is FRP rupture of the joint. First, both of them might have some advantages and disadvantages. And now let's look at what we had in this kind of behavior. Before going ahead, just some examples. This is showing kind of debonding case, FRP debonding. It of course depends on at which level this debonding occurs. If it happens very early, then it is not that meaningful. Debonding. If it occurs later at a large drift, then this could be kind of acceptable. And that's showing kind of a rupture of FRP on the joint zone. Again, it depends on the design, depends on the drift at which bit where the failure occurred. Here you see many different types of joint retrofits, but most of them are debatable according to me because most of them doesn't include some transverse beams framing into the joint, or they don't include the effects of the slabs mostly. So when you don't have these, firstly the behavior of unretrofitted specimen is underestimated. And also the contribution of FRP to the joint behavior is overestimated. So you can have significant enhancement in behavior, but it's really questionable whether this would be the same in case of field structures. And I could touch to the issue of joint retrofit in the codes. According to my best knowledge, this is only present in the Italian documents. They allow usage of FRPs for joint retrofit under certain conditions, and they also define an effective FRP strain to 0.4%, considered during design of FRP retrofit of joints. But that's all, I think. I mean, no other codes touch on this issue, and also the information about joint retrofit is that limited in Italian documents. So here I want to summarize some results on two groups of tests. These are two different PhD works. One of them I have mentioned is done by İdris Bedirhanoğlu on, I think, 18 beam column joints, which is full scale, which also includes some slabs as well as transverse beams. So you can apply only realistic FRP retrofitting schemes. And the other is Dr. Coşkun, who tested large, again, full scale, but this time three-dimensional tests, which totally represents the slab and transverse beam, etc. Basically, the purpose of these tests were somehow validate these tests in a larger experimental program. Again, the original specimens or reference specimens or pilot specimens have certain deficiencies, like concrete being low strength, as well as usage of plain surface reinforcing bars. So this shows the test setup of group 1 specimens. This is the column of upper story. This is the column of lower story, the beam, slab, and transverse beam. As you see here, we test the specimen in horizontal direction, which means that columns are horizontal now and the beam is vertical. These are the details. As you see, no reinforcing bars in the beam column joint. And I could say that the dimensions of the columns and the beams are 25 centimeters by 50 centimeters. This is quite, I could say, the full-scale member test or assemblage test. This is showing the instrumentation and loading pattern. Here are the results, I could say. Interestingly, the first specimen, which is the reference specimen, failed, basically because of slip of beam longitudinal bars first. I'm going to explain this mechanism in the next slide, which somehow gave us a kind of pseudo-ductile behavior until 4% lateral drift. Then we had the damage, significant damage on the joint, and the joint shear damage caused more more rapid strength decay in the post-peak area. This line shows the flexural strength of the beam. I should say that the strength hierarchy for this beam column joints is like that. The reference specimen has weak joints, so the most critical area is the joints. And then if we sufficiently strengthen the joints, then the next weak element member is the beams, and the column is the most strongest. So if we don't retrofit the joint, the failure is expected to be because of the joint, as obviously seen with this test result. And if we sufficiently can retrofit the joint, then the failure should occur within the beam. Okay? So that's kind of not a very bad behavior because quite sort of ductile, even if it is less than expected strength, then shear failure. Still, we could go up to large drift levels. And this explains how the slip of main longitudinal bars occurred. That's a kind of strange mechanism. When we apply tension to the top bars during lateral loading, we have a quite high concentrated stresses here, just around the hook, which caused crushing of concrete around this area. So, because of the crushing of concrete here, gradual crushing of concrete, the shape of the longitudinal bar, which was hooked 90 degrees, changed, like the yellow one. And of course, obviously, this caused kind of slip or kind of displacement of the main bar. So this is reflected by a large crack at the intersection of the column and the beam, and relatively lower strengths than you could reach when the beam longitudinal bars yield. I should say that obviously because of this slip type of behavior, the beam bars were not yielded, even though there was a big displacement at this point. This is kind of proving the mechanism that I want to explain to you. And then for solving the problem, of course, first case, we want to solve the problem about slip, not about the joint. So we wondered what would be if we solve the problem about slip, but not solve the problem about the joint. So what we did was just behind the joint, we broke the concrete on and under the hooks of longitudinal bars. And we first welded the hooks of bottom bars to the hooks of top bars, which were all bent 90 degrees up and down. And as a second intervention, we just replaced the concrete, the weak concrete here with a higher strength repair mortar. And nothing else. This was how we repaired for this one. And then the behavior was like that. We could reach higher strengths, but then, and we didn't have slip here, but then we had a joint failure in shear. As you see here, the joint damages were more severe, and the behavior is, I could say, more brittle with respect to the slip case. In case of slip, we had larger displacement capacity without losing the strength. Then, to solve the problem about joint shear damage, we applied different schemes of retrofitting using FRPs on the joint, which are totally applicable because this specimen has everything like the slab and transverse beam around it. And we applied different jacketing, I could say, schemes using FRPs. And then this is, for example, the result of one of the tests. As you see, no problem was seen within the joint. We could reach the theoretical strength of the beams in both pulling and pushing directions. And we could go up to about something like 10% lateral drifts, which probably will not be required during even the strongest earthquake. And as you see here, we had no damages within the joint. We had damages within the shear because this was the target. And if you wanted to eliminate this type of failure, you could retrofit this part as well. But often that's what we want. That's a desirable failure mechanism. We want the damages occur within the beam to survive the earthquake, to dissipate the energy. And this is what happened in case of this specimen. There's some slight damages on the column as well. But since the column was stronger than the beam, in this example, we didn't experience any serious problem. If column is weaker than the beam, of course, what you have to do, you should also retrofit the column as well. So this shows the test setup of group 2 test in terms of joints. Because I have limited time, I'm going to pass this slide more quickly. We had column axial loads on 4 of the columns. And then we applied the lateral loads here using these 2 jacks. The specimens were cut between the story heights. So this is kind of reflecting the moment 0 points at mid-height of the lower story. And that's the next story. And that's the mid-height of the second story, I would say. This is showing the details. As you see, again, there is no transverse reinforcing bars within the joint. Again, the strength hierarchy was similar. We had the most problematic area were the joints intentionally, and then the beams, and the columns were more stronger. So we expected damages first in the joint, and if you retrofit the joints, the damages are expected to occur within the beams rather than the columns. So in this case, we used a kind of real earthquake record, and we make a theoretical analysis and a nonlinear structural analysis, time history analysis, and determine the displacement pattern, and we just applied a certain part of displacement pattern to these specimens. And again, although we tested some more specimens, I'm going to summarize you the 3 specimens here. One is reference specimen, control specimen. One is the specimen which corresponds to the previous joint tests, which we only weld the hooks of top bars and bottom bars to each other and no FRP retrofit. And finally, again, another 3-dimensional specimen which corresponds to the joint that I have shown you before, which we have also weld to avoid slip, also FRP on beam column joint to avoid beam shear failure. And I mean, the conclusion is here given as a summary. Again, we had some kind of slip and then joint failure in the reference specimen. And when we avoid slip by welding of bars and also replacing the concrete, weak concrete around the hooks of longitudinal bars, then we had shear failure in the joint. And then when we do both, which means when we also weld the beam bars and also we use FRP sheets on the joint, we could reach to beam flexural failure, which was we targeted. These are similar with the beam column joint sub-assemblage test, so I'm not going to show details. If you have some questions, I can come back here, but what have been done is, as I said, welding of hooks of main bars, as well as replacing the concrete just behind the joint core. And this shows how we retrofit the columns. We apply different techniques, but this is the one of the application technique that I'm going to show soon in the next slides. And this shows the appearance of the retrofitted frame, 3-dimensional frame. And this is the behavior of the reference specimen. As I said, very similar to sub-assemblage tests. We had much lower strength than theoretically expected strength because of slip of beam longitudinal bars because of joint of the damage due to concrete crushing in front of the hooks of longitudinal bars. And then we had joint damages, joint failures somewhere here, which is not a very bad behavior, but it is the strength is much lower than we could expect. And this is the one which we had the welding, not FRP retrofit. Again, we had this time better strength, but less ductile behavior because of joint shear failure, increasing drips. Too bad, again. And finally, this is what we obtained when we have both the precautions in terms of slip, avoiding slip, and also to improve the shear strength of the joint. So we could observe perfect behavior. Again, this time, as you see, we didn't have any damage on the joint, and all the major damage was accumulated within the beams. And this was, as you know, the expected failure mechanism. So with just few slides, as also mentioned in Italian code and several different papers, we could determine the strength of FRP retrofitted joints by making use of simply the horizontal equilibrium equation. But the issue is that when the bonding could occur, or what should be the effective FRP strength should be taken into account as, because it changes according to application types. For that, different researchers have recommended different values. And here's the value that we could obtain based on the tests that are shown here. So you could go up to 0.4% strain very, very usefully while you retrofit the joints. And then you can design how many plies of FRPs are required to obtain a certain joint strength. Anyway, there are other researchers as well. I want to conclude my presentation here, which I hope gave you a short overview of what we have carried out here in terms of retrofit of reinforced concrete columns and beam column joints. So thank you all, and I will be glad to answer your questions if you have any.
Thanks a lot for this very nice presentation with a large amount of work in the field of seismic retrofitting. So if any one of you have questions, you can ask them directly by the microphone or maybe by writing. So maybe I have one for you. You mentioned at the end that there is some design code. What's your opinion on there is in Eurocode 8 part 3 some basic first equation for FRP retrofitting, and I know that there is some working group trying to promote the use of this material. And there is not so many design rules for anchorage system. And since you have a good experience, are you aware about some design equation for such kind of anchor based on your experience?
I think that's a very tricky point. I mean, basically, I should tell that into my knowledge, I don't know exactly about this type of column retrofit. I'm not aware of any design rules for this kind of anchorages. And I know that there are some studies going on, but I'm not really sure whether they ended up with a kind of equation which could be implemented in the course. On the other hand, I should tell that this depends on very much on how you make the anchorages. So maybe before being able to provide some design equations for the anchorages, maybe the methodology of how we are going to do the anchorages is also very important, because I should tell you that we obtained very poor results if we applied conventional anchorage techniques, which means that if we drill a hole and if we try to anchor the FRP rod or FRP laminate within this hole, unfortunately, very probably because of difficulty of proper application within a very small hole, we got very, very weak results. So at the end, how we could obtain a good anchorage was to open a big hole, not a small hole which is opened by a rotary hammer, but just we opened a larger hole. And then we put the anchorages within the hole and used a very, very high strength grout. So this is how we could obtain a very good application.
Okay. So I see that someone is writing questions. You can, everybody can read it. Your feeling about dynamic or static loading. Yes, maybe based on all your experience with so many tests you have done, some have been done on shake table and some other maybe on quasi-static loading. What's your opinion about this?
Very good question. What we did was, and we did this during one of these joint tests, joint sub-assemblage tests, we loaded the specimens under different loading rates. So during earthquake, generally you are not sure of what the loading rate is, but what we did was we changed the rate of the loading, quasi-static loading. We loaded the specimen in a kind of quick way, like a dynamic loading. And then we applied a smaller rate loading, like the ordinary ones. Unfortunately, I didn't show this comparison of these two specimens here. But I think it's already presented in an ACI journal in 2010, I guess, or 11. So you can see the effect of different loading rates. And I should say that basically the difference was quite few. I mean, there is no noticeable change. So if we assume that the seismic loading is often not very high loading rate, very high speed, like if you have an explosion, the loading rate is very high. But in case of seismic, that's rather not that high. So I personally would not expect a very, very big difference related with loading rate.
Okay. So maybe last questions. Comparison with steel jacketing. Do you have any, since you have a good background on this, any comparison was done in Turkey from steel jacketing and FRP jacketing to see the difference?
Yeah, we have carried out this kind of work on different types of columns that I have not shown here. I should say that steel was, of course, better. But in terms of ductility or in terms of strength, in our case, steel jacketing was better. But, you know, steel has some other problems. I mean, mechanically, it's good if you properly anchor. That was what we had done in those tests. We had tested three types of jacketing at the test I have mentioned. We have used reinforced concrete jacketing, we have used steel jacketing, and we have used FRP jacketing. And I could say that steel jacketing was kind of expectedly was the best. But nevertheless, about protection, maintenance, etc., and other things, increasing geometry, sometimes FRP jacketing may be more preferable. And in practice, if you look at practice in Turkey, after 1999 earthquake in Turkey, about 17 years ago, there was a big rush in people to retrofit their buildings. And initially, very few people preferred steel. Most people preferred concrete jacketing because it was a little bit cheaper. Currently, people are more focusing on FRPs because of ease in application and not changing the geometry, and practically because of basically practical reasons, not because of mechanical reasons. Yeah, that's what I'd say.
Okay, thanks a lot. So thank you again for this very nice presentation. I will have to work on the file, and I think it will be available on YouTube during the weekend. So thanks a lot, and see you next time for this series of webinars. Thanks very much, Alper, and see you soon.
My pleasure. Thank you.
Have a nice summer.